Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you. Well, it's very nice to be here in Colombia, and what I'd like to do is tell you a little bit about thank you. So these screens don't show the same as up there. Okay, that's why I was slightly puzzled. Thank you. So I'm going to tell you about open science, open data, open source in the opposite order. So I'm going to start with open source and explain to you, I hope, some things that what you will see Microsoft is changing and responding to the needs of scientists and IT workers. So the topics today, I want to begin with a brief introduction to the way science is changing and the different disciplines within science. Then I want to talk a little bit about the role of open source in scientific investigations. I was in the university for 25 years, and it was a way we worked, open source. I then want to move on and talk about the scientific data, the challenges and the opportunities. So open data, I think, is really important for the furtherance of science, and I'd like to explain why I think that. And after saying some words about the open data agenda, I want to give some examples of open science which is engendered by open data. And then I'll end with a few words about where I see the future of data-intensive science and the sort of infrastructure that is needed to support it. So this is a familiar slide. We've all heard about the data deluge. It's a commonplace that in the next 5 years we'll create more scientific data than has been created in the whole of human history. Even the communications of the ACM, IEEE, Economist, Nature, and Wired magazine. Scientific methods obsolete. I don't believe that. That was saying all you need is a search on the data. That's not the case. You need modeling and you need theories. But nonetheless, it illustrates the fact that data is becoming a much more significant part of a scientist's life. And so I'd just like to show then 3 slides of my colleague Jim Gray on a talk he gave 2 weeks before he disappeared. What Jim identified, what he thought was the emergence of a fourth way of doing science. We're all familiar with experimental science, since people have looked at the stars in Egypt and so on. Theoretical science began with people like Galileo and Kepler and went on with Maxwell's equations and Schrödinger equation and so on, where you can explore those laws of nature, encapsulate a lot of experience from data and experiment, and then you can make predictions by analyzing mathematically those equations and then do experiments to check whether those are true. And so you can build mathematical models and then go and verify them. And that historically has been the 2 ways we've done science. Until about the 1950s, only 60 years ago, when electronic computers became of age. And they enabled a new way of doing science. And if you want to investigate climate change, for example, there is no way you can do experiments with our climate because we only have one. But you can do, on the computer, you can do simulations and try different effects, different models, different competing activities to see how that could affect the data. You can do experiments. If you want to know how galaxies evolve, how the universe evolved, how black holes can collide, again, you can't do these experiments. And the mathematical equations are too difficult to solve analytically. So what developed is a third way of doing science, which Nobel Prize winner Ken Wilson in the 70s called the third paradigm, by which he means in order to do computational science, which complements, not replace, theory and experiment, you need to understand numerical algorithms, you need to know numerical methods, approximation techniques, you need to know about computer architecture, parallel programming, and so on. A whole set of skills that isn't traditionally taught to people in the traditional theory and experiment. And what Jim saw was that today we're seeing the emergence of a fourth set of skills that are needed, namely to do with data-intensive science. Scientists are now overwhelmed by huge amounts of data, as you saw from those magazine covers, and the data comes from sensor networks, it comes from high-throughput genome sequencing machines, it comes from Large Hadron Collider, for example, telescopes. All sorts of inputs are now generating data at a rate much, much faster than ever before, and scientists are now becoming overwhelmed with data. And so in order to deal with this data, to manage it, to organize it, you need different sets of skills, and you need to know, in this slide, I've called these set of skills e-science, if you like. It's about dealing with distributed, data-intensive, networked science, which is often collaborative. Even if you're doing social science research, you can't store all the data on your machine. You have to go to this database, combine it with this database, put them together, and so on. So lots of disciplines are affected by this, and maybe it would be better to call it e-research. But this is another slide from Jim. He saw the emergence in each discipline X, so let's say biology. He saw that there were two distinct sub-disciplines. One was computational biology, and the other one was bioinformatics. And that's, for example, the center we're setting up, the government in Colombia, is on computational biology and bioinformatics. And the problems that scientists have to deal with is getting the data in the first place, cleaning it, making sure that not obvious miscalibrations and errors. And then you have to manage this, moving it around. Then you have to organize it, but then you may have organized it wrong and reorganized it. How do you share it? How do you visualize it? All sorts of problems that you need to be able to do. You need skills to do it, and you need the tools in order to help you do that. And this is Jim's vision of the future, where we have access to all the literature, we're familiar with the literature being online, but increasingly you will need to also link the literature, the papers, scientific papers, to the data that was used to create the results. And actually being able to navigate from the literature to the data, and then combine it with other data sets enabling new discoveries, is how Jim assembles his pyramid. So you have in the middle here derived and recombined data. People may put data that they didn't have anything to do with creating with other data and make new discoveries. And that's one of the things that will actually power science in the future. And you'll need to make sure that people who create the data get some credit, like you get a citation on an ordinary publication. What do you get for data? How do you recognize people who create data sets that are useful? And just to emphasize again, when I joined Microsoft 6 years ago, Craig Munday, this was his vision, and it's very similar to Jim's. Data-intensive science doesn't replace the other three paradigms, and increasingly, as this conference's theme makes clear, computing in both the data sense and the computational modeling together will help speed up science, reduce time to insight. And so this is a sort of representation of how you put all these skills together, of course with theory and experiment. So that's where we are. Let me say a little bit then about the role of open source. So, open source tools for science. Researchers often need to develop tools to do their analysis, to do their visualization, and there aren't any commercial options. And one of the things that the community like to do is to share tools, to actually have other people extend them and create them. So you try and build a community where you actually build a bigger and better tool by having different people contribute. And funding agencies, often because it's public money that have funded this research, demand that the software created on it is actually released to the world because it actually is paid for by people's taxes. So increasingly funding agencies are requiring that software produced by a project they fund should be open source. Now, when I was Dean of Engineering in Southampton, I used to have people who were very keen to make a business. So they had this great software and they wanted to make a business. And they'd chosen an open source license. And what is important to be aware that there are many, about 50 or so, open source licenses. But they're roughly of two types. And which type you choose determines whether you can make a business of a traditional kind or whether you have to do a service type business. So understanding the difference between software licenses is important for researchers if they want to start software companies, for example. The other thing that I was involved in, I was on a funding agency called JISC in the UK. I was on their board, and we funded lots and lots of open source projects. And they were great. They did lots of interesting things, but they were then given to the world and put into SourceForge. But that doesn't automatically guarantee that the software will continue to be useful, because when the postdoc or the graduate student leaves, unless you've documented and tested it and make sure that it runs on this machine and that machine, it's very difficult. And most projects in SourceForge just die because they never reach the critical mass. So that's what scientists must do, is decide which tools they want to make live and to build communities around. And that's an important part of the open source process, getting people to buy in, to share and to extend. So this is my committee I ran for JISC. This is one of the things we produced, a report on open source licenses, and talked about 50 licenses and just listed a few. So there's GPL type licenses, and there's Berkeley BSD licenses and Apache. And the difference between BSD and GPL is important. If you want to actually, my engineers came to me with their software, and even if they put all the effort that they wanted and got lots of venture capital making that software really easy to use, if they'd chosen a GPL license, then they'd have to put all of that extra work back into the public domain, even though it wasn't funded by public money. So if you want to build a software company, the choice between a BSD style license and GPL is critical. And it doesn't matter what they choose, but they need to actually understand that they're making a business choice at that moment. This is an example from the US, the National Institutes of Health, the National Cancer Initiative. They listed just 3, GPL type and BSD. So these are the common type, 2 types of licenses, GPL-like and BSD-like. And they're important choices if you wish to take your software that you've carefully created and make a product like MATLAB or Mathematica that people want to buy. You need to choose your license carefully. So what is Microsoft doing in this space? Well, Microsoft has realized that we have to interoperate, and people have mixtures of systems, and they may use a bit of IBM, a bit of Oracle, a bit of open source, a bit of Microsoft, and you have to, interoperability is very important, standards, and the fact that you can use open source with commercial source is clearly important. So Microsoft have set up a foundation. They're a founding member of the Outer Curve Foundation. We don't own it. I'm a board member, but we're outnumbered on the board. It's a not-for-profit. It enables Microsoft employees to work on open source projects. So what it enables is that Microsoft people who work for Microsoft Research or for the Microsoft product groups can go and work on open source projects in this foundation, who own the IP and so on, and without upsetting Microsoft and the lawyers and everybody else. So it's a mechanism by which Microsoft can contribute to the open source development of tools for science and so on. And this is a nice quotation from Dr. Dobbs, Adrian Bridgewater. Microsoft has, over the last 18 months, open sourced most of its community developed projects and technologies via the Outer Curve Foundation, the not-for-profit software IP management and project development organization. So the Outer Curve Foundation is where we're trying to put our community projects, and what we have to do is to build up a critical mass so these can be used and supported by the community without dying and never being updated and so on, and taken further. So the Outer Curve Foundation has a metaphor it uses from museums. It calls them galleries, and galleries have specific topics. So we've started a gallery called the Research Accelerators Gallery, and in that our team have put, at the moment there are 3 offerings. One is a workflow tool called Trident. The other one is a chemistry add-in for Word, and I'll say a little bit about them. And another is a project called Conference XP, which is a real-time collaboration connecting people, a tool for doing that, which is run by academics, and even though we started it, now that collaboration is take on, they develop that in ways that they want to take it further forward. So Project Trident is a scientific workflow. Increasingly you want to do a whole sequence of complicated things, and you want to make sure that you record what you've done. So you want to capture what's known as the provenance. What was done when the data set, what has been done to it from when it was taken raw data, what are the various processes, and can you document exactly what's been done for that data set. And you can automate that. You go and do this, then you do that, then you take data from here, and so on. So workflow tools are becoming increasingly important in biology and also in environmental science. And then this is a product which sounds trivial. It's about doing chemical equations in Word, but it does more than that, because it actually uses chemical markup language, which captures the sort of meaning, captures the semantics. So when you type in CH4, the computer has enough information, it can recognize that the C and the H are a carbon atom and 4 hydrogen atoms, and give you the choice of either calling it methane, CH4, or giving you the chemical structure picture. And it has enough information. So if you like, it's the beginning of semantic chemistry. So these are a couple of the projects. The project that we've had a workshop on this week, and that we will be looking at in this conference, is what used to be called Microsoft Biology Foundation. This is going to be submitted to the Outer Curve Foundation, and because it's not Microsoft who's running it, we didn't want to call it Microsoft Biology Foundation. The Outer Curve Foundation didn't want to call it a foundation in a foundation, so we had to call a new name, and the name that we now have chosen is called Biodex. And it's an open source bioinformatics library, so it can be taken, they can be extended, they can run on different platforms, file parsers, writers, algorithms, and so on. And it focuses down at the low level for assembly, manipulation of the DNA sequencing data, and there's a board that helps steer where we should go, what are the key libraries, key routines we should put into this library, and we're transferring ownership and any IP to the Outer Curve Foundation. And you can find out more about that in the demos and the talks at this workshop. One example of a project that we're doing with David Heckerman and his eScience research group is looking at biofuels. This is a project we're doing with collaborators in Brazil, looking at how you might increase the yield of ethanol from sugarcane if you understood its genome. Sugarcane has not been sequenced, it's a very large genome. The energy from sugarcane is 6 times that of equivalent amount of corn, but it's predicted that you could increase that still further, but we need to understand what the genome is and how one might modify or change it. And so we're developing algorithms to sequence from the sequencing to assemble it to understand exactly what the genome, and these algorithms will be again in the public domain into the Biodex library. So those are some examples of the open source activities, and again those projects typically will be led by, not by Microsoft, but by university professors and communities, and we wish to see if we can establish a critical mass that those communities can thrive and build interesting and useful tools that work with our Microsoft products to enable scientists to do their work. Let me talk a little bit then about open data. And I'd like to give one example. We saw Worldwide Telescope demonstrated today. An earlier project from the Sloan Digital Sky Survey. This was one of the first projects to do a large survey. Instead of a professor and 2 students going to a nice place like Hawaii, where there's a telescope, taking data for a week, if it isn't cloudy, and then taking it back to their university laboratory, where they'd spend the next 2 months writing up a paper. This is an automated system, you can see it there, which scans a quarter of the night sky. And from that, in very high resolution, over the last 10 years or more, they've collected a large amount of data, 300 million galaxies, roughly speaking. And you not only have pictures, you also have the spectra. Alex Zale at Johns Hopkins with Jim Gray decided to build a web service called SkyServer, which makes that data available. And so making the data available has some interesting changes. So you can go and download and examine the data, and around about 400 million hits in 6 years, and has about 1 million distinct users, which is very interesting because the astronomy professional astronomers are around 10,000. So it shows there's a great deal of interest from the general public in understanding and looking at this wonderful data. It's led to some serious papers, 1,600 referees papers, but it's also been used for delivering educational to high schools and showing the galaxy in different ways. It's interesting, it also is a new publishing paradigm. There are 10,000 astronomers, there are 300 million galaxies in here. And you're obviously not going to look at all of those things before you publish. So the data is published before all of it has been analyzed. And I'll come back to that later. But making the data available really changes things. Catherine Van Ingen was in Jim Gray's group, and what she set out to do was to do something similar with the environmental science community. And we've heard today with the biodiversity and climate and so on that hydrology and water are going to be very vital things in the future. So she's been working with Lawrence Berkeley Lab and the Berkeley Water Center, setting up a web service, not for stars and astronomy data, but for environmental data service, environmental science. And so by working with different communities, they've managed to put together a service which is now building a community. And it's more than building a community, it's changing their style of working. So in the FluxNet organization, they have individual flux towers which measure various parameters like temperature, like moisture vapor, like the CO2 movement on these towers. And typically they're owned by a professor, and again, just like the astronomer, the professor and 2 graduate students would write up the data from their particular tower. By putting all that data into a web service, first of all, you can see all sorts of anomalies and inconsistencies that you have 2 towers which are only a few miles apart, which differ very greatly in terms of temperature, for example, in which case there's some calibration problem. So you can find out errors very quickly. But also, the data is taken every 6 hours, and it's stored in files. And if you want to get a weekly average from this environmental sensor, then it's very easy. You send your graduate student who spends a very miserable time getting all these different files, assembling them, and giving you the answer for the weekly average of this. By putting them into a data server like this, you actually can do all the cleaning, and you can make it so that even professors can go and analyze the data without abusing their graduate students. But it also involves a different sociological change. Instead of a professor and 2 students authoring a paper, it's much more useful to do 10 environmental towers, and that means when you write your paper, you have 10 professors on it and 20 graduate students. So instead of a 3-author paper, it's a 30-author paper. And this is a different thing. Different communities are having difficulty coming to terms with this sociology. Particle physicists now do papers with hundreds, or even now with the new LHC experiments will be with 1,000 physicists on it. But other fields are not so keen about such large-scale collaboration. So what we're developing here with the Flux Data site here is actually the beginnings of a new community. So fluxdata.org is building together communities in Europe, in the US, and around the world around these flux data centers, and it's an interesting experiment in sociologically as well as in science.
So I have talked about the data, making it available. That's one of the things, but you'll find the astronomy, for example. You can find a paper which analyzes some data. It is estimated that only in about 10% of the cases can you, as a reader, go and get the data on which that paper was based on. So that makes it very difficult to sort of verify or reproduce science. And so Jill Nesiroff at the Broad Institute of MIT, this is a paper from Science last year, she talks about as user computational research grows, new tools are needed to expand recording, reporting, and reproducing the methods of science. It's very difficult then to claim that this is a real science if nobody can reproduce your results. How can you make the data available? And so reproducible research is very important. So we work with Jill with the Broad Institute with their database called YinPack to link that to their publication. So the publication now has embedded in the data, and you can check if it has been updated by running a workflow from the document and update the document, and the people can take the paper and extract it, so you can actually go and see if the data has changed, if the conclusion has changed, and so on. So this is, if you like, a first step in reproducible research, and this was specifically connected to the gene pattern database, but now is Trident, where you can use this with any particular document. So reproducible research is a key part, and when you have taken all this data, you need to do something with it, to store it. And so the word librarians use is curation. So they're working with the California Digital Library to build an add-in for Excel. Scientists often use Excel to store their data. But what we're trying to do here is trying to give support for versioning, for timestamps, ability to check shared vocabularies. Biologists, for example, use ontology, which is a specific word, specific for their discipline, and so you want to be able to create and add in to the data and notations and metadata through the database. So this is a tool where you'll be able to do that and also help you deposit the data and the metadata directly into a data. As we'll see later, the NIH, if you're applying for research for the National Institutes of Health, they demand that your proposal includes a data management plan. What are you going to do with the data at the end? How are you going to make it available to others? That's now being adopted by the National Science Foundation to what everybody asks. Then I'm going to say by data. These are important questions that need to be answered, and this is a talk to help them put the data into a form that can be used by other people. So, this is a working process jointly with the Loan Foundation. And this is a project that started from a drink in a bar that I had in Northern Holland with a Danish librarian. And it's about, the problem is that many of these issues have everything in an electronic form, but then actually electronic form sounds better and much more modern, but actually is much more vulnerable to loss. So this week in the UK, they're celebrating a week of digital reconstruction at the Doomsday. This day was done by William the Conqueror in 1066. It took the first census of the UK when he conquered the UK. And inspired in this story, for which I keep a book I still read, I passed then to another fact I observed during the 1970s. I mean, in the 1970s, it was thought to be a good idea to make a modern digital version of the Doomsday Walk. And they did that. They made a wonderful thing that had videos, they had digitalized forms of the Doomsday, and they had interviews and so on. And they did it from the state of the art of, and probably had never heard of it. It was the BBC man-made computer with a special video disc player. It was discovered 20 years later that there were only 2 machines in the country that could still read this modern digital version. So they did some digital technology, if you like, to take this old version and convert it to new modern formats so we could still run them in a machine today. Well, the same is true with all versions of documents. The National Archive in the UK is extremely aware of what has been called digital black hole. Old versions of documents like WordPerfect or versions of Word, so converting them into modern documents based on that channel, which you could use any tool you like, to any format you like, TOF, UOF, or whatever format. That's how it started. And this is now the Planet Foundation to help meet digital preservation challenges with a solution that is widely adopted and actively practiced by national heritage organizations and beyond. The OPF believes that establishing digital preservation practice requires an open community that actively shares best practice and is able to apply group learning. It also believes that making tools available under an open source license, where and when it is possible, will stimulate the adoption of the digital preservation practice. So, Microsoft Research is a member of this foundation. They're looking at what to do with the data and how to create it, and we have to preserve at least some of it. So, these are some of the issues that go along with data. And this is an award that we sponsored. It's called an Open Access, published by Biomed Central, and the Open Data Award. And data sharing, it says, is an increasingly important part of research in the fabrication process. This award recognizes researchers that have demonstrated leadership in the sharing, standardization, publication, or reuse of biomedical research data. And here is Alex Waite and Peter Murray-Rost in the picture, accepting the Open Data Award on behalf of the biology and data for the article, How Common is Ecological Speciation in Plant-Feeding Insects. And Peter Murray-Rost is relevant because he and a group of people have put together what they call the PANTOM principles to open data in science. And PANTOM is named after a place in Cambridge that basically it's believed that science is based on building on, reusing, and openly criticizing the published body of scientific knowledge. For science to effectively function and for society to reap the full benefits from scientific endeavors, it is crucial that science data be made open. So this is one of the awards that we sponsored. What I've been talking about until now is scientific data, and I really think I should backtrack and say that really research is more widely directed than just for the science and engineering disciplines. It is also for geographers, sociologists, and historians, and this is a project that we've been doing with Professor Walter Alvarez from Berkeley. And he's a geologist. He's the one who gave the theory that dinosaurs were killed by an asteroid impact. And what he wants to do is put on a scale that we should go from geological timescales to civilizations to biological timescales, put them all together and see if we can find correlations and new ways of looking at history. So if we want to, you can find out by looking at the chromosomes. So we're taking that and we're actually trying to develop a tool to enable you to do what's called the history. So here, this is showing on the left the evolution since the Big Bang. And then at the top there, the expanded shows the beginning of life. And then at the top right there, there's human life and then there's civilization as we know. And it's huge time scales. What we're developing using some of the Zoom technologies we are now familiar with is a tool that enables you to do this type of research. And I would just like to show you how you might transverse sooner or later on this short video.
Here we're looking at an example of periodizing history. In this example, we're using Italy, and the first big division you can see is pre-Roman Italy, and post-Roman Italy. So thanks to Zoom technology, we can zoom into any one of these boxes to look at them in more detail. So for example, in Roman Italy, if we zoom in here, we'll see that's divided into early Rome, the Roman Republic, and the Roman Empire. This is just an example, so we're only providing one source. But in the future, we hope to provide different sources of different interpretations of history. Let's take a closer look at the Roman Empire. So what we've done down here is we've represented all the different emperors with little pictures or statues. So if we go into one of these, for example, and look at Hadrian, Hadrian is also a really good example of how there's really no limit to the kind of resolution that these images can be. So here's a quite large resolution image, which is really just a small part of this map here. And if we look over here, for example, here's a panoramic. Vesuvius. And these can really be gigapixel images, and that is images that are greater than 1,000 megapixels, or 1 gigapixel. So, but again, that's just one small part of this entire document. Another fun thing we can do is we can embed papers. So if we look down here, we've got a paper talking about the periodization of history. This is an entire PDF, and any part of it you can zoom into. And you can do so without any delay of having to scroll, tediously through a PDF. And of course, one of the great benefits of figures, they remain sharp, but they're also very quickly and easy to browse, more so than using this in a standard PDF reader. High resolution images, again, can take place. Here we are looking at an outcrop. And if we had a gigapixel image of this particular outcrop, we could zoom down right onto the ground and look at an object right on the floor. In this case, the marker. For now, though, that's just an illustration. And one last fun thing we can do, we go back in this paper here. Every paper has references. So here's the references cited of this paper. The tedious thing about finding the additional references, you have to first open them and download perhaps and open in its own reader. With zoom technology, let's say we're looking at this paper here, also by Alvarez. What you do is if you spy down here, you see that the entire paper is actually embedded right here also. So without any delay, we can keep zooming, and this is a full PDF in full resolution. We can look at any one of these diagrams if we wish. And again, we zoom out, we can see it's just a small portion. You can watch it there going away of the original document, and the original document is just part of this historical Italy example.
Okay, so that gives you some example that it is not just scientific data. There are all sorts of data that are being able to navigate it and visualize it and explore it in new ways. It's not just for the scientists. It is also for sociologists, historians, and whatsoever. So I think it is very exciting. What about the emergence of open science? So let me say a few words about that, and I'll use a few examples of what we have discovered when we were doing a report for the NIH. And this is a very interesting example to me. It's about rapid data sharing. It's about researchers that are looking for biomarkers for a disease. So, it was launched in 2004, and it was unusual that there were multiple centers, and instead of keeping it all private, they actually made a conscious decision that would be all put into a central database, which would be made public. And so, not only could it be combined quickly, but because other centers were doing it, there were incentives, and typically they would make publicly available. They would not wait for 6 months till people wrote papers. They were available in about a week since the day they were collected. And hundreds of scientists have now made use of this and many downloads from their websites. And the interesting thing to me is that the subtle thousand paper that have been using this data, a significant number of those were authored by researchers who were not directly funded by the project. So you have the concept that you can win the Nobel Prize with data that you didn't take. So you need to make sure that people who did took the data can get some credit. And I'll come back with that in a moment. So this is to me a very interesting example of how sharing data, consciously sharing data, has accelerated the publication. It has accelerated the way we do science. This is another interesting example done by the U.S. Geological Survey. It was looking at whether you can use the Landsat photographs along with the data on how the pollution and water wells. And what they were looking at, when the decision was meant to do biofuels instead of rotating crops of corn to soybean to corn, they decided to do as more economic, to do corn, and not the alternation. Well, that's fine, except that corn requires much more nitrogen fertilizer than soybean. And so, what can you find by doing this together? By looking at what the crop patterns were and what the pollution data, you can find what the cost of the policy was. Well, the cost actually is polluting subwells, and you need to do something about pollution of the water. So this is the value of information. By putting these different data sets together, they were able to come to some cost of this government policy and estimate the relevant costs, that is, polluting the water. And this is another example of the coastal ocean observation technology. Scientists and raptors, they were looking at radar data, which looks for the variation data of the ocean waves, surface waves, and so. And that's why they were putting out data. They were making data available and serendipitous and expected the use by the U.S. Coast Guard. Because historically, when the ship sank, they used land chart covers and so on to figure out where the person was. But they can now do much more accurately by using this data that was accumulated in the earlier time from this database. So again, making data available allows people to use it in unexpected ways. And just one last thing is the quote of the bottom, Professor Scottfield. How did he get funding to put equipment into the ocean, but not to analyze the data on the back? They had to throw a lot of the data away because they can't afford machines to store it. So again, I think the funding agencies are now rethinking about, is that a sensible thing to do? Should we use the cloud? One of the options is not sensible, to pay a lot of money to take the data and then to have it to throw most of it away. So, interesting examples, I hope. And lastly, I talked about SkySurvey and the fact that there was a lot of public interest in exploring the data. And I think it's because it is becoming increasingly important that scientists make it clear to the general public. Taxes are paid for that research. So why is it interesting for the public? And also see if they can understand to be involved in the research and see for themselves and its web support. And so it is stunning the fact that despite the number of galaxies who took the Sloan data, that is 300 million galaxies, there is only 10,000 astronomers who cannot look at every one of them. So they asked the general public to help them in classifying the galaxies. Whether they were elliptical, whether they were spiral, whether they were spiral to the left, to the right, they gave them some guidelines on classification. And to their surprise, they now have 200,000 individuals and many tens of millions of classifications of galaxies. And so, this is enabling people to get excited and interested by science. You can do it as a school project, you can do it as a community project, all sorts of possibilities. And happy real discoveries have been made in scientists' major papers, one of which is the subject here. Hanny van Arkel is a Dutch school teacher, and his blue object here is not an error in the photography. It is the bluest galaxy anybody's ever seen, and the question is, what is it? Alexei has now space-time to go and look at that. So it's called Hanny's foreboard, which is the word in Dutch for object. So it is possible for citizens to be involved in doing real science. When I arrived in 2005 in Microsoft, Bill Gates was giving a talk at supercomputing that was being held in Seattle. And he gave a talk on the importance of data and how science is going to be transformed. This is one of the slides that he used. And it's actually a very good vision of where science is going. If you just have a paper, it's static and inert. What you would like to do is click on the graph and actually change the visualization. Look at it in some different way. Plot something different. And incredibly, the way, for example, my friends the chemists get data from the papers that are published. They take the paper, they have a copy of it, and they take a ruler and they measure on the graph of the paper the data points, which is really ridiculous because you should be able to click on the paper and go straight to the data. If there's a graph going through it, which is a curve from the model, maybe you'd like to click on that curve and find out what the curve was. Maybe you want to do some different experiments. So again, reproducible research going to the data where it was imported, the data may change. And that's again the sort of broad example and less peer review is much more important for science and enables science to have a sort of quality bar. But there are maybe other things that you can do. There are the social networks, Kobayanet Central, and they have one called Faculty of 1,000, and it is these people who comment on what they felt was the most interesting paper last month. So you can choose to follow different people. You don't have to follow all of them. You may say, well, Tony Hay's suggestions are not very interesting, but Rick's, on the other hand, are really worth following. So you can choose your own social network to see of the papers rise as important. Well, in biology, when I last looked, there were 2 papers a minute. Every minute of the day during the 365 days of the year are deposited in PatNet, and nobody can keep up with 2 papers. So maybe you need some help. Maybe having a recommendation service is one part of that. I say you need to be aware of giving credits, and so there's an organization now called DataSite, which is trying to make the research data a first-class publication, because people don't get credit by often publishing data put into net to the data, and notations that are useful to others. So there has been an increased acceptance for the research data as a legitimate, citable contribution to the scientific network. Interestingly enough, in the Sloan Digital Sky Survey, they found a paper which really wasn't very much. It's just the fact that it was new data, but it was really a summary of what the real new data was and had, 1,000 authors on it. And so one of the authors was a graduate student, and he was no longer in the deal of that, but he's now one of the most cited astronomers ever because of these data papers. So citing data is important. Similarly, there was a change of publication styles of authors like J.P. Hay, and I call myself Tony Hay, but it's not the same person. So then, it's about how you need a unique identification for researchers and be able to actually disambiguate these words. It is important, and that's the goal of ORCID, to solve the name of the authors, and I think that's important for the establishing of credits. So, I believe there will be a lot of different types of researching passages. These are things that can be centralized, but they can also be distributed. In Latin America, you have CAITO, which can change the publications, and we have a translation service and translate from Spanish to Portuguese to English or whatever language. In the future, not only it will contain the full text of the paper, but also the greater literature that comes from workshops, papers, conferences, search reports, theses, and citations. But in addition, I think we'll also see data images and software also contained in these large researching passages. So I think we'll see centralized ones, and I think we'll see ones which are federated among universities. Let me give you some examples. A centralized one, which is a National Library of Medicine, and a federated one, which is an organization called Worldwide Science. So let me show you that. So, the National Library of Medicine in PubMed Central, if you get a grant from the National Institute of Health to do some research, you will be able within 12 months to put that text of that paper in the public domain. Can you publish in Nature and Science, whatever, but after 12 months the public has paid for this research and the public should be able to see it. And that's how the National Institute gets the full text of all papers. But in addition, the National Library of Medicine has wonderful databases, so it has databases on genome, protein sequences, and so on. And what you can do is exactly what Jim envisioned. You can go from the publication to the data, to another dataset, to a publication, and you can put different data together. In fact, David Littman, who is in charge of the PubMed Central, believes that where too long fade in cross-fade database search. You can sit down with the biologists and within a few hours find something interesting, a new discovery, by linking data from different data sets. So that's really, if you like, a very highly curated wall garden where everything's carefully controlled. But most people don't have the luxury of that. And so, most people have different communities. They don't have the money to make a centralized one, so there will be distributed ones. And this is a particular one, initiated by the Departments of Energy of Scientific and Technical Information, whose job is to make the U.S. Department of Energy data available. And so, they put together this consortium, which now has 65 nations. It has large numbers of papers and datasets. Some of them are obvious, some of them are not so obvious. And you can type in the query Microsoft Translator. For example, we translate it from English to Chinese. We go to the Chinese data source, and it will get the results translated back to English. And you get them in English or Russian and so on. It's really very interesting, the federated search tool. It has a search engine that goes across all these federated databases. And the interesting thing is the statistic that I got. You put them together, and when you compare the search results using their federated search engine, which is looking at datasets which are not necessarily visible to a web search engine. So they are not necessarily HTTP sites and so on. Only 3.5% are found by Google and Google Scholar, and the rest is unique to worldwide science. This is the invisible way because a lot of data is currently not sought by the usual search engines. So again, if you want to actually accelerate science and accelerate discovery, therefore, understanding what to do with search invisible sites and how you put them together for search is going to be important. So I talked about the volumes and rapidity of publication, the fact that we're going to need some help, and some computers are great for storing and computing and doing all that sort of stuff, and Microsoft and Google index the web daily, but in the future we'll need much more help. We will need help by acquisition, interpretation, influence, analysis, and all this sort of stuff, and we'll need computers to help do that. And that means the computers have to have some understanding, some semantic information about what's stored at that site, why it is stored in this paper, if this is about the star you're looking for or maybe some other star, if it has to have some hints and some clues on how to do that. And so one of the projects we have at Microsoft Research is a project called Inner Eye. Antonio Criminizzi is doing this, and it is looking, in this case, medical sense, and it is using machine learning techniques that we talked about to try to understand if we can automatically detect specific fissures without having to say next step. That's the carotid artery, and those things are not to do with that. So it can detect and understand from an image which of the parts are relevant. So that's an example of trying to put some semantic information, semantic computer in there, in this case using machines. So what I'd like to do now is show you a short demo of this, which is its entity, and you'll see there's a demo later on, which is semantically enabled with this sort of software. So why don't I ask him to come and give a short demo? And you have 7 minutes starting right now.
Muchas gracias, Tony. Es un verdadero honor estar aquí con todos ustedes en esta hermosísima ciudad de Cartagena. My name is Oscar Naim, and I am going to describe Sentity in 7 minutes exactly. Sentity is a research output repository platform that provides a suite of building blocks, tools, and services that help you create and maintain an organization's digital library ecosystem. With Sentity, researchers can easily access, analyze, and unlock the previously hidden structure and relationships among data elements, as well as extend existing data models by adding additional relationships and properties to these relationships. Sentity is flexible and extensible, taking advantage of the optimizations of performance features available from Microsoft SQL Server 2008. Describing your data is something important because it allows entity to get it to make some sense of it. What you may see on the screen here is an example of that, and you see two pictures. Let me tell you about the data. This collection here is a set of demos that have been presented since 2005 until 2011, and an event called TechFest. And TechFest is an event, a Microsoft research event that is celebrated every year and encompasses all the leading edge that have been done for the particular year. So we put all the data and we enable it with this entity. Second thing that we see here is a tool called the Pivot. Pivot was created by Microsoft Live Labs, and it is now part of Microsoft Silverlight. And the beauty and the power of Pivot is I'll ask you to visualize all the national data, one nation at a time. Or, all interesting enough, is also completely diagnostic. So it doesn't matter whether you have, let's say, in this case, demos, or there could be museum objects, or, biology thesis. Well, it's exactly the same tool. Now, you've seen a lot of demos about sense and all of that. Well, those technologies are also available here. So if you have an object that has a very interesting image, you can actually very easily see it here. Now, the odd thing, you might think, okay, but isn't that, say, a candy? No, actually no, because you can easily just by selecting the by clicks. That answers the question. So, for example, with this graph, here immediately you recognize that the number of demos presented at TechFest have been written at, are about all the same label every single year. Oh, that's great. Now, if we go here to the left and select the contact names, you see Eric Harris being quite a successful contributor to the TechFest. And in fact, Eric has about 21 contributions, and you see them all along the different years. I would show what happened in 2010, but I will ask Eric later on. The other thing that you can do with this is that you can search.
Now, if we go here to the left and select the contact names, you see Eric Horvitz being, quite a successful contributor to TechFest. And in fact, Eric has about 21 contributions, and you see all the contributions along the different years. I'm not quite sure what happened in 2010, but I will ask Eric later on. The other thing that you can do with this is that you can search. So let's see what happened to actually Sentity, and see if Sentity was presented at TechFest. And yes, indeed, I click on this, and then on the right here you have all the metadata associated to that particular object. If I click on Sentity 2.0, I go to the actual page in researchmicrosoft.com about Sentity. This is all live information, and this is all out of the box, by the way. By you defining the data model, which is how you describe your data, Sentity was able to make sense of basically everything. So there is no magic. It's all about how you define your entities and the relationships between those entities. Now let's say, this entity thing looks very cool. I would like to find out more about it. Well, I go to contacts and I select the contact person, who happens to be me, and we go to the person collection, and there we have a picture of me. Great, and then you see all the different areas that I've been working on, and you see that I work for Microsoft Research Connections. I select that, and now I go to the group page, where it tells you, all the contacts that the group has, the mission of the group, the different areas. And, Rick mentioned the Worldwide Telescope during his presentation. And let's say that you want to find out more about that, and you know that Dan Fay is the contact person for that. We find Dan here. We select Dan. We go to the people collection again. And then we see the Worldwide Telescope. And indeed, Worldwide Telescope was presented at TechFest. And in fact, that was a very cool demo using Keynote in order to be able to drive the experience that you saw in the demo. So that's great. Now, but what else can I do with this data? So let's for a second search for Sentity again. If I can type, of course. There we go. And you notice here there is another tool called the Visual Explorer. Being able to visualize your data in more than one way, it's extremely important. I would say it's critical, because how do you know what's the right way to visualize data? And we cannot assume that it's going to be one way or another way. And in fact, right now we have two different tools, visualization tools with Sentity, Pivot and Visual Explorer. But the important thing is that the platform itself enables you to add any more tools going forward. So that's critical. Here you see a graph that represents the search that you were making as the central node, and then everything that's related to that node. So you can ask the question, what else is related to this thing? And then because of the relationship that you have defined in your data model, you will see all of them like that. Now, the reason why I wanted to show you this is because, well, Sentity has a video, and one of the cool things about using Pivot Viewer, which is, again, an extremely cool technology from Microsoft Live Labs, is that if you have media, you can actually play that media embedded in your Pivot Viewer, as hopefully I can show you here in a second. My name is Oscar Naim, and I am so I could actually give a video of my own demo. It gets very weird. But anyway, so finally, I just want to, because I think I'm getting very close to my 7 minutes, I would like to say a couple of more things about Sentity. One, if you want to find out anything more about Sentity, please go to researchmicrosoft.com/Sentity, and that's our project page. And there you can download for free not only the binary version of Sentity, but also the source code. Also, in mid-June, we're going to be releasing Sentity 2.1. And I encourage you to please visit Lee Dirk's presentation tomorrow at 11. And during that presentation, we're going to show the results of a project that we did with the Universidad Jorge Tadeo Lozano in Bogotá, where we created our first deployment of Sentity in Latin America. And we are very proud of what we were able to achieve there, and very grateful to the university for all their great work there. So this version of Sentity is going to have a few very cool new features, and it is going to include localization to Spanish. So we are going to be able to see all the messages and everything in Spanish, so that's great. And the next step will be perhaps Portuguese, and who knows. So with that, I just want to say that Sentity is like a canvas, and you are the artist. So it's completely up to you. Gracias, Tony.
Thank you very much. Thank you. Well, it gives you some idea of, again, some form of adding semantics, adding ways of organizing data. So just let me finish then about the future of data-intensive science with a very few quick words. So I was co-opted. It was the oldest trick in the book. They called me up at NSF and they said, Dan Atkins has agreed to co-chair this, if you will. So I said, well, if Dan's doing it, okay. But I didn't know. They said to Dan, Tony Hayes agreed to do this, if you will. I should have realized. Anyway, so, and my team, Jim Pinkelman, Darren Green, and Evelyn Viegas were the team that helped put this together. So we made a report building on the communities about what we should do NSF about data-intensive science, and I'd like to share with you our advice to NSF about what they need to put in place to support data-intensive science, and I think it's relevant to any country, UK, Latin America countries or whatever, the sort of structures you need to put in, and I'll be very brief. So the recommendations of the task force looked at 6 areas: infrastructure, cultural, sociological chains, roles and responsibilities, economic value and sustainability, data management guidelines, ethics, privacy, and intellectual property. And so infrastructure delivery, it was really acknowledging that data infrastructure and services are essential research assets which are fundamental to today's science. To acknowledge that you shouldn't have just money to go and get the data, you should have money to do something with the data, and specific budget allocations for the establishment and maintenance of research data sets and services. So that's one of the principal recommendations. Cultural and sociological change, that's about giving people credit for doing data sets, norms and practice for citation and attribution, so data producers actually can get rewarded, and that there's a career path for data producers, data curators and so on. Roles and responsibility. Data stewardship is shared among many people. There's the principal investigator, but then there's the research centre, there's the university librarians. They have a role to play, I believe, in their repositories where they will store some of this data. Discipline-based libraries and archives, national scientific agencies. Some agencies like NASA actually do have a data deposit and they make their data available. Commercial service providers, how do they all mix together in this? And really the agencies need to be clear about that. And again, economic value and sustainability, realistic cost models. What's it actually cost? You can't save all your data, but what does it cost to go and take it again? Well, you can't take measurements of the temperature of the Pacific 20 years ago. That's just a one-off thing. You need to be able to keep it so you can compare and change. But there are some things, if you do a simulation on a computer, it may be cheaper to do the simulation again than to store the data. Data management guidelines, what are the best practice? When you ask for a data management plan in a proposal, you really need to tell the academics what that means, and if you ask them to put the data somewhere, where are they going to host it? What are the sites available? How are you going to support that, and so on. And of course there's ethics, intellectual property, and invest in the idea of privacy preserving data access, so that the investigators can embrace privacy by design. And again, interesting topics of computer science research. So the conclusion I'd like to come to is two slides. One is from Paul Ginsparg. The particle physics community from which I came have a tradition that they actually do peer review in physical review and so on, physics letters, physical review letters, but they also put their papers before review in an archive. So it's an unusual process that it's not peer reviewed, but it's widely available, and that's used by most branches of physics, mathematics and astronomy and so on, and it's used every day by all these people. And actually the physical review has learned to live with that, and not terribly happy, but nonetheless that's what their community, who are physical review, they're the people who are the American Physical Society, it's their users, they're the people who want this service. So this is what he says. On the 1 decade timescale, it's likely that the more research communities will join some form of global unified archive system without the current partitioning and access restrictions familiar from the paper medium, for the simple reason that it's best way to communicate knowledge and hence to create new knowledge. And then the last sentence here, ironically, it's also possible that the technology of the 21st century, we no longer need the printing press to disseminate, we can use the web and so on, will allow the traditional players from a century ago, namely the professional societies and institutional libraries, to return to their dominant role in support of the research enterprise. So interesting ideas. And since my 1 minute left, this is the last slide. So openness is in fact, I believe, a critical component if we wish to make data-intensive science a reality. We need standards for provenance, curation and preservation. There must be a default that you share data unless there are very good reasons, and there can be, for withholding it for a certain period. The publication processes need to change. Funding agencies must understand the cost of creating tools and software and tools to view and explore and manage the data, but also places to store the data, and data infrastructure and services need to be elevated to being recognized as core assets. And I think that's advice not only for the US, but also for where I came from, the UK, but I think also for countries like Colombia with its new vision of biodiversity, and also other countries in Latin America. I think these are things that are well worth thinking about. Thank you very much for listening.